welcome back to the JakeJoshTeam channel, and today we are continuing our near-coastal exam prep for the third mate unlimited tonnage license. Okay, today's subject is going to be on exact azimuths. So without further ado, let's jump right into this. Alright, so the 2018 U.S. Coast Guard question reads this. On 17 May, your 1554 zone time DER position is latitude 26, 33 minutes north, longitude 65, 46 minutes west. At that time, you observed the sun bearing 269 degrees per standard compass. The chronometer reads 07 hours, 55 minutes, 47 seconds, and the chronometer air is 1 minute and 14 seconds fast. The variation is 3 degrees west. What is the deviation of the standard magnetic compass? So, just reading from the question, you know there's a lot of information given, and this is one of the longest problems it's going to take to solve on the near coastal exam. But like anything, start the problem out trying to solve with the knowns. So, we know that the date is May 17th. We know that our zone time is 1554. We're going to have to turn that in GMT time. Our position is latitude 26 degrees, 33 minutes north. Longitude is 65 degrees, 46 minutes west. And then we know that we observed the sun bearing 269 degrees per standard compass. And we know that the chronometer reads 07, 55, 47 seconds. We know our air is 1 minute, 14 seconds fast. And our variation is 3 degrees west. And we're trying to solve for what the deviation is. So there's multiple steps to solving an exact azimuth problem. But the first thing you want to do is you want to remember that you need to find the latitude, the LHA, and the declination. So in order for us to find local hour angle and declination, we need to know the date and we need to know the time of when we observed the sun at 269 per standard compass. In particular, we need to know the Greenwich Meridian time, the GMT time, at which we observed the sun at 269 per standard compass. Alright, so like I said, we need to find the time, and the problem gave us a chronometer error, it gave us a zone time, so we need to use all those numbers together to figure out what our GMT time is, specifically up to the second. That's how accurate we have to be with an exact azimuth. So our chronometer reads 07 hours, 55 minutes, 47 seconds. The chronometer error was 1 minute and 14 seconds fast. Now, I did a previous video when we were doing time ticks about this concept, but whenever you're comparing a chronometer to the chronometer error and you're adding and subtracting times, any error that's slow, you're going to add to your chronometer. Any time that's fast, you're going to subtract from your chronometer. So, the problem said it was fast, so we're going to go with subtracting the time that was given to us. And when you take 07 hours, 55 minutes, and 47 seconds, subtract it from 1 minute and 14 seconds, our real chronometer time is 07 hours, 54 minutes, and 33 seconds. Once you get that, make a little note, put it on the side. Now that we have our real chronometer time, we know that the minutes and seconds we're going to be using to find LHS is 54:33. And it's a good way to check, because you can take a look at this and look at your zone time, and you can see our zone time is 15 hours, 54 minutes. So we know we're on the right track. We're going to get to this right GMT number. But now we have to take our zone time and convert it to GMT time. So when you're converting your zone time to your GMT time, it's critical that you use longitude to find out how many zone times we have to either advance or retard to figure out where GMT compares to zone time. If we're in a western longitude, we're going to add our zone description, our zone time hours, to our zone time. And if we're in an eastern longitude, we're going to subtract from our zone time. Alright, so we need to start with our longitude. So our longitude was 65 degrees, 46 minutes west. And we need to divide it by 15 because 24 hours times 15 degrees equals 360 degrees. The Earth is divided up into 24 time zones. You divide that by 360, 15. That's where we get the number for define our zone description. Okay, so moving forward, we know that we're dividing 65 degrees by 15, but you can't divide the minutes. So you got to take the minutes and convert them into degrees. So there's 60 minutes to an hour. So 46 divided by 60 gets you 0.7667. Just round that up, we'll call it 0.77. So our longitude is 65.77 degrees west. Now you take this number, and like I said, we divide it by our time zones. And when you take 65.77 divided by 15, you get 4.38 west. And remember, you just round to the nearest whole number. So 4.38 is closest to 4. It rounds to 4. So it's 4 zone description west, which means we're going to add our 4-hour zone description to our zone time to find our GMT. So we have our zone description plus 4, so zone time plus 4 because it's west. Our longitude is in western degrees. So zone time 1554 plus 4 gets you a GMT time of 1954. And GMT time is always recorded in military time. And I put this note down, civilian time 754, because 1954 military time is the same exact thing as 7:54 p.m. civilian time. Where do we see that number before? Our real chronometer was 07:54 minutes 33 seconds. Remember, all clocks go from 1 to 12. There might be some clocks out there that go 1 to 24, but all standard clocks, all chronometers for that matter, go from 1 to 12. So they make 2 full rotations on the clock every day in a 24-hour period. That's why your chronometers will only read numbers between 1 and 12, which is why I put the civilian time down as the note. We know that our chronometer real time was 07:54:33. Our GMT time is 1954, or civilian time 7:54 p.m. So those numbers match. So we know our math is correct when we do this. So what you do from here is you take your GMT time from the hours and minutes, and you take your real chronometer for the exact seconds, and you put them together. So that means our GMT time when we observed our sun at 269 was 19 hours, 54 minutes, and 33 seconds. And when we added this 4, we didn't go over 24. And if you go over 24, that means that you're in the next day. We didn't go over 24. 15 plus 4 is 1954, so we're still in the same day. That means May 17th is still the date we're going to use when we look this up in the Nautical Almanac in order to calculate our LHA. Alright, so now that we have our GMT and we know we're observing the sun, we can now begin to calculate our LHA. But the first thing we have to find is GHA, which we can find using the Nautical Almanac of the year 1981. In the Coast Guard license, every problem you're going to deal with is going to be from 1981. This will be provided for you on the exam. So what you're going to want to do is you're going to want to go into your Nautical Almanac on May 17th and find the hours of 1900. So you take your Nautical Almanac, you open it up, and it's organized by the date, so it's very easy to find. So you'll flip open to May 17th, 1981, and then it's going to have this list of hours that go down. Now I know you can't see it from the camera, so I'm going to add a little picture and talk over it here. But what you're going to do is you're going to get on there, and you're going to go down to May 17th, and you're going to find the 19. And that 19 represents what our GHA is. So coming back from that picture back here, we're going to find our sun's total GHA by adding the sidereal hour angle to the Greenwich hour angle. Fortunately for us, the sun has none. So we just need to worry about the GHA hours and the GHA minutes. So you cross that out. If you were solving for a planet or a star, you would use this, you would look for the SHA. And there's a tab section on every page, on every date, that says SHA. And you just go down and you find that star, and all you do is you take that star and you just take that number and get ready to add it to GHA. But we're dealing with the sun, so we don't need to worry about adding sidereal angle. So on that page I showed you on that picture, 19 hours was 105 degrees and 55.1 minutes. Now what we need to do is, now that we've found the hours, we need to find the minutes and seconds. So our minutes and seconds is 54 minutes and 33 seconds. So to get that broken down into degrees, what you're going to have to do is you're going to have to go to the back of the Nautical Almanac. And there's a section in the back that reads increments and corrections. Again, you guys can't see this, but I will put a picture up and talk over it. And what you're going to do is, when you're looking for your increments, you go to the page that has the minutes, and then you just go down on those minutes on the second section to the number of seconds we have. So here we have 54 minutes and 33 seconds. So on this page, on increments and corrections, I go from 54 minutes down to 33 seconds. And we are going to be adding 13 degrees and 38.3 minutes. So coming back from the picture, now you can see how the math looks now. So we're going to add our GHA hour, our GHA minutes and seconds. We don't need to add SHA because the sun doesn't have an SHA. That's only for stars. And you take these, you add them together, and you get a GHA total of 119 degrees and 34 minutes. Now you take GHA and you're going to add or subtract from what your longitude is to find your LHA. Alright, so our GHA total was 119 degrees, 33.4 minutes. Now we're going to subtract our longitude because our longitude is west. Now, this is different from the zone description, so don't get these mixed up. Now, when you're dealing with GHA, any degrees that are west are going to be negative, and any degrees that are east are going to be positive. So we had a longitude of 65 degrees 46 minutes west. We take that, move it down here, and we're going to subtract it because it's west from our GHA. So GHA minus our western longitude is going to get us our LHA. 119 degrees minus 33.4 minutes minus 65 degrees 46 minutes west gets you an LHA of 53 degrees 47.4 minutes. And with that, we have found our LHA. So now we have our latitude, we have our LHA, Now the only thing we need to find is our declination. So for declination, we're going back into our nautical almanac. I'll put the picture back up again as I go through this, but I want to show you how I shuffle through the book. So remember, we're on May 17th, GMT 1954-3. So you're going to open your book until you get to May 17th, and on May 17th you go down to the 19 hour. Now you'll zoom in and take a look. So for declination of the sun, in the sun section, you'll go down to declination and you just follow the declination down and you match it to the 1900 hour. So as we can see as we go down, we're in northern latitude, 19 degrees, and everything that's right of the N19, those are minutes. So the minutes that are right next to the 19 hours are 26.1. And I'll bring it back here. So we're going to put our declination is 19 degrees and 26.1 minutes north. That's important. And then we need to find the D correction because it's not exactly 1900 hours. It was 54 minutes and 33 seconds. So back to the picture. You're going to go all the way down to the bottom of the sun section and you'll see a D and a 0.6. That is the D correction. Back to the board. 0.6 is our D correction. So what's that mean? Well, that means we need to find out what our real correction is with 0.6 at 54 minutes and 33 seconds. So what you're going to do is you're going to go back to the increments and correction pages in the back of the book, the back of the nautical almanac. You're going to find the page for 54 minutes. On this page, if you scroll over, you go sun, planets, Aries column, moon, planets, then you get to V or D correction. That's where you're going to find your correction. So looking at the picture, V or D corrections, you're going to find your D and you're going to scroll down to where it says 0.6 on the left-hand side. So I have it circled. So 0.6 is on the left-hand side, and what's right of it? Right of it is 0.5. That is the number we're looking for. So back to the board. So you found 0.6 and the number next to it is 0.5. We're going to add 0.5 minutes to north. And the only reason we add is, I'll take you back to the picture again for May 17th, is because when you are scrolling down, you scroll from top to bottom. When you scroll down, the numbers in the declination are getting bigger. So if the numbers are getting bigger, you're going to add that correction you found in the D correction tabs. And if the numbers are getting smaller from numbers that are at the top of the page, you'll subtract that number. So that's how we find what we need to add or subtract to our declination on the hour. So here, it's 19 degrees, 26.1 minutes north. We're going to add 0.5 because that was the correction associated with 0.6. And now we found our real declination, which is 19 degrees, 26.6 minutes. And with that, we have found our real declination, our LHA, and our latitude. So once you know your exact latitude, your LHA, your declination, you won't need any other information. The only other information you're going to need to keep track of is where we observe the sun and the variation. So on the exam, you're going to get a book, Sight Reduction Tables for latitudes 15 to 30 degrees. This will be given to you on the exam. This is the book that they always test from. So you're not going to get any latitudes that are above 30 or any latitudes that are under 15. Latitude will always be between 15 and 30 degrees. So you'll be using the sight reduction tables, but not yet. What we're going to do is we're going to create a chart that's going to help you figure out what pages you need to go to in the sight reduction table to acquire your correction for the per standard compass. So our latitude is 26 degrees 33 minutes. The first thing you're going to do on this little spreadsheet you're going to set up is you're going to take these numbers and you're just going to put them in for what their degrees are. So just take this and go 26 north, 53, and 19 north. Okay, so once you take your real numbers and you turn them into degrees, this is the keys to the page you're going to flip to. So I'll put a picture up on the screen here, but first I'll show you how I flip through it. So you're going to pick up your sight reductions, and the first half of the book, the longitude numbers are on the very top of the page here. And once I show you the picture, you'll see it better. The longitude numbers are on the very top. The first half of the book is divided from degrees that are 15 to 22. And the second half of the sight reduction table are degrees that are from 23 to 30. So we know that we're going to have to go to the second part of the book and use latitude 26. We'll also know that in the top left and the top right corners of these pages are numbers, LHA, and it says right next to it when you look at the picture. So LHA is in the top right or top left corner depending on what page you're on. And that is the page we're going to find our base azimuth, our base Z. So you flip open, you find LHA 53, and you find degrees 26. The next thing you need to do before you look at the declination is you need to look at the latitude of the declination and the latitude that we're sailing in. If one is south and one is north, you go to the contrary side of that LHA page. If they're both north, you go to the latitude same side. So we go to page 53 LHA with 26 degrees latitude, and we go scroll down the page on the declination until we find 19. You take 19 and then you scroll over until you get to the 26 latitude, until those two numbers meet. And the number that is under Z, that is going to be your base Z. So that Z that we found on that sight reduction page, you're going to make another column and you're going to put 86.7, 86.7, 86.7 on all the base Z's. So now that we found our base Z, now we got to find the respective Z's. And when I say respective, we need to find the azimuth that is in between 26 degrees and 27 degrees at the 33-minute mark. So to find the azimuths, to find the respective azimuths, what you're going to need to do is you're going to need to go back in the sight reduction. So the same way we found the base Z is exactly how you're going to find the respective Z. So when you do this, take a look at your numbers and write what the numbers are between. So 26 degrees and 33 minutes, that is between 26 degrees and 27 degrees. 26, 33. So when we found the base, we found for 26. If it's between 26 and 27, the respective Z we got to find for latitude 27 degrees. So I'll put the picture back up, but just scroll through the book how I said. Open up the book to the LHA page that we're finding, and then look up at the latitude, and then this time we're solving for 27 degrees because 26 degrees 33 minutes is between 26 degrees and 27 degrees. We already found 26, so the respective is going to be the other number. the number that your main number is between. So go from 26 degrees and just skim over to 27 degrees, and then go to your Z, and then scroll down to declination 19, and that's your new base. And on the picture it shows 87.6. So back to the board, 87.6 is our respective Z for latitude. Now we continue on, and now we got to find the respective Z for LHA. Well, LHA, we had our base at 53, and 53 degrees, 47 minutes. Is between 53 degrees and 54 degrees. So this time, we're just solving for LHA. So this time, everything's the same. We're just changing LHA. Just like last one, we changed the latitude. This time, keep latitude the same, keep declination the same at the bases, and then just change 53 on the degrees. So like I said, I'll put the picture up here. Just scroll to the book. Now this time remember, the latitude is 54 degrees. So flip to the 54 degrees page, and then go to so LHA 54, same declination, go to latitude 26, and then compare it with the declination 19. You scroll those together, and you should get 86.3. Back to the board. 86.3. Now we just have to do this one more time. Now we're just changing declination. Keep latitude at the same degrees, keep LHA at the same degrees. We're just changing declination to find the respective Z. So declination was 19 degrees. Our real declination was 19 degrees, 26.6. So that's between 19 degrees and 20 degrees. So this time you keep the same latitude, same LHA. So you're going to 26 degrees north, and you're going to LHA 53 degrees. But the declination that we're going to use this time is 20 degrees north. So, just like we did on the past ones, and when we were finding Z, flip open to LHA, page 53. Degrees, go to the degrees 26. And remember, we're just changing declination, and then just go one number down from 19 to 20, and go over and get to the column that matches 26 degrees with 20 degrees, 26 degrees latitude and 20 degrees declination, and you will get 85.5. Back to the board. 85.5. And that is how you find the respective Z's. Now the next step is much simpler. The next step, you just got to find the difference between the Z's, and you just subtract the two numbers. So when you find the Z difference, you take your respective Z and you subtract it to the base Z. So treat your bases as negative numbers and treat your respective Z's as positive numbers. So when you're solving for base Z on the latitude, just write negative 86.7, positive 87.6. And then the difference between these two is positive 0.9. And that's what you would put in for that one. Then you do the next one for LHA. Just do negative 86.7, and we're comparing it with a positive 86.3, and that'll get us a negative 0.4. And then go on to declination difference. Just do the negative 86.7 compared to the positive 85.5, and that's going to get you a negative 1.2. So you just fill them in, negative 0.4, negative 1.2. So now that we have the z difference, we need to find the increments, because we're going to multiply these two numbers together and then divide them by 60. But before we get to that, so an increment is pretty much the minutes of anything on a degree. So for example, 123 degrees, 54.6 minutes, the increment would be 54.6. So the increment for latitude, 26 degrees, 33 minutes. We just put 33.0 minutes. The increments for LHA, 53 degrees, 47.4 minutes. Put 47.4. And then the increments for declination, 19 degrees, 26.6 minutes. Just pencil in 26.6. Okay, so the formula for finding your corrections, the correction, which is z difference times increment divided by 60, I've put right here. So what you do is you take your corrections, and if your z difference is positive, your corrections will be positive. If your z difference is negative, your difference will be negative. So for latitude, positive 0.9 times 33 minutes divided by 60 equals positive 0.5. So you do that math out, and you put it in there. And then for LHA, negative 0.4 times 47.4 divided by 60, you'll get 0.3. Always round these up to the nearest number. And then for declination, negative 1.2 times 26.6 divided by 60, it's going to get you approximately negative 0.5. Now once you have these corrections, you're not done yet. You need to take these corrections and you need to add or subtract all three of them together. So you take these corrections, add and subtract them together. Positive 0.5 minus 0.3 minus 0.5 is going to get you a real correction of 0.3 degrees, and we will be applying that to our base z. Alright, so you take your base z, which was 86.7, and you're going to subtract it from the correction we got from these guys, which was 0.3. You take 86.7 minus 0.3, and your z is 86.4 degrees. Now, you're not done yet. You got to know what quadrant, what part of the world you're dealing with. So, based on our observation, our declination was north. So, we're north 86.4 degrees. But we also need to know our longitude. Well, our longitude was 65 degrees west. So, our longitude was west. So, our azimuth really is z north 864.4 west degrees. So, in the site reduction table, I'll put another picture up really quick here. But in the like center of the book, the center top on the left page and the center bottom on the right page, you get this little note that says north latitude. If your LHA is greater than 180, then your azimuth is what your azimuth is. In the north latitude, if your LHA is less than 180, then you need to take 360 and subtract z. Whereas in the southern hemisphere, if your LHA is greater than 180, you take 180 and subtract it from your your Z, your azimuth, and if LHA is less than 180, you take 180 and you add to your azimuth. Something you need to know, because remember our LHA when we solved it was 54, and we were in the northern latitude. So that means we fall into this category. What we have to do, the correction we have to make, which means we fall into this category. LHA is less than 180, so we need to take 360 and subtract it to 86.4 degrees. So you take 360, you subtract 86.4, and you're left with 273.6 degrees. We're going to use this number and compare it to what we observed on the sun on our per standard compass. So now that we have our azimuth that we found, 273.6 degrees, we need to find the difference between that and the observed sun on our per standard compass to find our compass error. So the difference between 273.6 minus 269.0 is 4.6. So 4.6 degrees is our compass error. But is our compass error west or is it a compass error east? So the way to know that is draw yourself a diagram, a compass for that matter, north, east, south, west, and draw whereabouts your Z is and where your per standard compass observation is. So for us, our sun was observed at 269, and our Z was observed at about 273.6 degrees. So relatively, that's what it would look like if you drew it out. And what you do is you go from Z to per standard compass, Z to per standard compass. And depending on the direction you go, that's how you're going to know which direction your compass error is. So anything that goes clockwise on your compass rose is west. And anything that goes counterclockwise on your compass rose is east. So for us, Z dropping down to per standard compass is going to create a counterclockwise direction, counterclockwise motion. So if it's counterclockwise, going from Z to our observation, we know our error is east. So the difference was 4.6 degrees, and we had a counterclockwise rotation going from Z to per standard compass. So we know it's 4.6 degrees east is our compass error. Now we can use our compass error and the variation of 3 degrees west to find out what deviation is. Alright, so we found our compass error, and remember, compass error always equals variation plus deviation. When you combine your deviation variation, that's your compass error. So our compass error was 4.6 degrees east, which equals our variation. The problem told us our variation was 3 degrees west plus deviation. That's how we're going to find compass error. So this is just simple math now. So I always like to treat west or east as a positive or negative number when I do this. So for this one, we'll say our east is positive and our west is negative. So we need a number minus 3 to get us 4.6. Well, 4.6 plus 3 is 7.6. So if you use 7.6 east, because that's our positive number, minus 3 degrees, or 3 degrees west, gets us 4.6 east. And then you can just look at that, and if it makes sense, you're good to go. And just looking at it, it makes sense. 7.6 degrees east combined with 3 degrees west is going to throw us closer to the west. And it's going to get, when you combine those numbers, you're going to get 4.6 degrees east. So the answer to the problem is our deviation is 7.6 degrees east. And that is how you do an exact azimuth problem.